period of time. We'll figure that out also. So all of those things go into our perception of some stimulus. Okay, everybody got that? All right, let's take a look at modality. How we determine the modality. Well, that's all based on the receptor type. If the photoreceptors in the retina of our eyes are sending information to our brain's going to assume that that stimulus was light and not sound or touch or some chemical. Okay? So the modality that we perceive is really based on the receptor type that's sending the original message. Okay. All right. What about location? How we determine where a stimulus occurs. What's the origin of the stimulus? Well, our body knows where our receptors are. Right? If a touch receptor in the palm of my left hand sends messages to my central nervous system, my central nervous system assumes that that stimulus occurred out of the palm of my hand, because that's where the receptor is. And so that's how we figure out where the stimulus occurs for these different stimuli. That works for a lot of these, but what about for hearing? Right? How do we know where a sound is coming from? Right? So our ears give us information about sound, but that's not the source of all the sound that we hear. It's not coming from inside, well, some people may inside the heads, but it's coming from somewhere else around us, right? So how do we figure out where a sound is coming from? Anybody know? Let's hear it. I did not mean for that fun. I promise.
Your brain can actually decipher between the time difference of when the sound reaches one ear versus the other.
That's right. So you use two different ears when you listen, right? And each ear is in a different place. So if a sound is coming from my left, those sound waves come along, it slams into my left ear first and then my right ear. All right? There's very little difference in time, right? Sound travels pretty darn fast, right? The speed of sound goes really fast in the air. But there's enough time lag between the two ears that our brain's able to process that and figure, okay, if there's this much time between when one ear hears it versus the other, then that must be at this angle off of the center line. And so that is how we tell if something's coming from the left or from the right, and how far to the left or how far to the right. What about, let's say you're in a swimming pool or in a lake, and you dove underwater and you're sitting there at the bottom, and you hear a noise. Right? Like, I don't know, the noise from the motor on a boat. Right? You can hear the turbulence around the prop and so forth. Can you tell which direction that's coming from?
No.
No, why not? Still using the same two ears, the same distance apart.
The medium's different.
The medium is different, that's true.
The waves are faster.
The waves are faster?
Like, I think that the sound waves in the water travel faster or something like that.
Something like that, yeah. Yes?
Does it, like, the sound waves, like, are not able, they either are bouncing off everything in the water, that means it's blurred, or it's, like, not bouncing off anything at all?
The sound is different, right? But the key is the speed that sound travels through water versus through air. It travels a lot faster through water. So fast that your brain is not able to see the or to determine the difference in time between when your left ear hears the sound and when your right ear hears the sound. So you can't tell what direction the sound's coming from. You can tell if the sound is coming closer or further. How do you tell that? What's that?
It's louder.
It gets louder, right? The pitch will change too, a little bit of Doppler effect there. Right? So if you hear the motor, it goes, and you think, oh my gosh, it's going to hit me, and you can't see it. Right? That's when you lay really flat on the bottom, right? Until the noise starts to fade, and then you go, okay, it's going away from you. But you don't know what direction it came from or what direction it's going to. And that's because the sound travels too fast in water for our brains to figure that out. Okay? All right, so here's our little picture of a person's head, and somebody's tooting their horn at them. Right? In this case, since the sound's coming slightly from the left, it's going to hit the left ear a little bit before it hits the right ear. The brain's able to figure that out. Okay? So that's what you need for sound. Questions about that? All right. Another little trick we have to help determine the location of a stimulus is lateral inhibition. This relates to touch, right? If something bumps into you, say it hits your skin, it stimulates receptors there and you can feel it. But when something pushes on your skin, you're actually stimulating a lot of receptors in that area. Your skin sort of bends down, and so all those receptors around there also get stimulated. Right? The ones in the middle get stimulated the most, the ones outside of that a little bit less, and so on. But it gives you kind of a blurry idea of where exactly that stimulus is, because all those other receptors around it are also responding. But lateral inhibition helps to sort of shut down or lessen the response of the surrounding receptors to help sort of magnify the ones in the center where the stimulus actually occurs. Let's see how this works. All right, so we've got 3 receptors here embedded in the skin, and a stimulus is going to occur right in the middle. So it actually stimulates neuron B, but it also stimulates A and C a little bit. And if you look at the action potential frequency that's generated by all 3 of these neurons, B has the stronger, the highest frequency. A and C have something less than that, but they're still responding. Right? Remember, that's how neurons code for stimulus strength, is with action potential frequency. We talked about that a while ago. Okay, so we can say, oh yeah, B is a little stronger, so the stimulus is more in the middle. But if we can exaggerate the difference in these frequencies to make this one higher relative to the ones on the side, it makes it even easier for us to pinpoint exactly where that original stimulus occurred. And so these frequencies are happening right there at those receptors, but further along the chain of neurons, we get this lateral inhibition. So here's our receptor B, generates this relatively high frequency of action potentials. A and C, they generate action potentials, but at a lower frequency. And they send their messages along to their axon terminals. Right? And so they'll send it along and it keeps passing on all the way, let's say, to the brain. But the axon terminals branch, so that B here synapses with another neuron that actually inhibits A's line of neurons and C's. It's going to inhibit the neurons around it. And so it inhibits it, so it slows down its action potential frequency, or lessens the action potential frequency. Right? A is going to do that also, but because it had a lower frequency in the first place, it has less effect there. So yeah, this frequency is a little bit lower than this, but B, since it had a higher initial frequency, has more of an inhibiting effect on the neighboring neurons. So what does the brain actually get? It gets this relatively high action potential frequency from neuron B and a really low frequency from A and C. And if you look at the difference there, it's a very large difference in terms of what the brain gets a hold of compared to what we originally had. It's magnifying this effect, it's making it easier for you to determine, yeah, B is really where that signal occurred, and A and C is not where that touch occurred. How do you guys feel about lateral inhibition? Does that make sense?
You said it was an axon? Like, can you describe again, like, the anatomy of it? Like,
Can you
what
describe the axon? That's pretty funny. So all 3 of these are going to send action potentials along their axons, and so
Right.
these green lines are representing the axons. But the axons split into these different axon terminals, right? So we have a diverging pathway here. So this one neuron B communicates with this red neuron, this green neuron, and this red neuron. So whenever this neuron fires, it sends messages to all 3 of those neurons.
But then most actions go, it's just happening
That's where the initial stimulus is.
and everything's getting filtered out.
And we're trying to filter out A and B. That's noise.
Yeah.
It's distracting us from what's really going on.
What's the purpose?
What's that?
What's the purpose of it? Why do we need it?
Why do we need it?
Let's go with B and like give it strong.
Why not keep it real? Go with the original? So one could, but you see here the difference in those action potential frequencies is not as great as what we have up there. And so when your brain is trying to figure out, okay, where on your arm is this? Say, a mosquito starts to bite you. Mosquito's tiny, and if you look at its little proboscis, it's really tiny. And you want to go ahead and flick this thing, but not even look, you just want to go ahead and flick it. Well, is it in this area, or is it right there? So by filtering out or lessening the signal from these neighboring neurons, it's much easier for you to pinpoint exactly where the original stimulus occurred.
So it is to specify the exact point, right?
It helps us to specify that exact point, yeah, or to narrow down the likely area of stimulus. Okay, anything else?
But does it depend on the location on how this inhibition, the lateral inhibition kind of works? Like you said, like last time when you had like the two, like pointy, like compass things like on your back.
Compass things, we call them points.
I'm bringing up one of them.
Yeah, I do know what you're talking about.
But where the points are not, you're not able to determine exactly like, is there's 2 points or if there's 1 point on your back compared to something that's like on your arm where there's a lot more sensory receptivity.
So remember, that was more related to the size of the receptive field for each individual
Right.
receptor. And because on your back, those receptive fields are much bigger, you can't tell within that area where something is, unless you start getting overlap of receptive fields, which you do a little bit. But because the receptive fields are larger, that alone makes it harder to pinpoint it. So sure, you could say, yeah, it was neuron B that originally sent the message. Well, neuron B covers a big area. Where in that area? I don't know.
And
Yes.
Is this specific for touch?
Yes. Anything else? All right, we got that. This is just another way of representing what we just talked about. Here we're getting stabbed by a pencil, and the center neuron is going to take most of the stimulus, and we've got this lateral inhibition going on to sort of shut down the neighboring neurons. The blue curve at the top, that shows what the response would be without lateral inhibition. Yeah, you get this little peak in the middle, and then you get some messages on the side. But with lateral inhibition, you can see it's greatly exaggerated. The difference between where the actual stimulus occurred and the neighboring areas is much higher. And so it's easier, again, to pinpoint where the original stimulus occurred. Right? Sort of the same thing, just drawn a little bit differently. Okay. Let's move on to intensity. How do we know how intense the stimulus is? How do we perceive the intensity? Well, we already know this. It's the frequency of action potentials. The higher the frequency of action potentials, that correlates, in most cases, to the strength of the original stimulus. Another contributing factor is the number of receptors activated. So if you get a gentle touch to your arm, only a few receptors are activated. But if something big bumps in really hard, it's going to stimulate lots of receptors, and that's going to be interpreted as a much bigger initial stimulus. Okay. All right, so this is diagram here. This is showing how the change in stimulus is correlated with action potential frequency. If your skin is bumped by a glass probe and it's barely touched, then you don't get any response to it. It didn't reach threshold. Pushes in a little bit, it might stimulate that receptor a little bit, and you get some action potential frequency. Pushes in further, higher frequency. The bigger the initial stimulus, the more that probe pushes into your skin, the higher the frequency of action potentials. Larger stimulus, higher frequency. This shows that the number of receptors activated. So a small stimulus might stimulate only one receptor or just a couple. If you get a bigger, stronger stimulus, then it'll start to stimulate more neurons around it. And that codes for a larger initial stimulus. Questions about that?
Is it higher frequency of receptors or higher frequency of neurons?
Higher frequency, the frequency part is related to the action potentials sent to the central nervous system. Anything else? All right. How do we determine the duration of a stimulus? It depends, right? So we're going to talk about two different types of receptors that sort of respond to a long duration of stimuli in different ways. And keep in mind that most receptors are somewhere sort of in between the ends of this spectrum, right? So consider this the ends of the spectrum that we're looking at. All right, so we have some receptors that are slowly adapting or tonic receptors. Slowly adapting or tonic receptors. So these receptors give you continuous signals. As long as the stimulus is still there, they keep sending messages. All right, so if I go to push on your arm and it's stimulating tonic receptors, as long as I keep pushing, you're going to keep sending messages to your brain saying, yeah, this guy's pushing on my arm or whatever, and it's getting annoying. Okay. Let's go ahead and look at figure 4 of this. All right, so the bottom curve here, all of these are over time. The bottom curve represents the stimulus, and the vertical axis represents the strength of that stimulus. So the first arrow is where the stimulus comes on. It persists for a while, and then the stimulus is removed. So here we have the receptor potential. This refers to the gradient potentials. Right, as soon as the stimulus comes on, we get our gradient potential, and that persists until the stimulus goes away. And we get action potentials in response to that. Right, so we get action potentials right in the beginning, and we keep sending action potentials. Yeah, the frequency lessens over time, and eventually you'll learn to ignore it, and it'll stop responding, but it's sending messages the entire time the stimulus is there. Okay? All right, the other type, fast adapting or phasic receptors. Question in the back?
Yeah, for the slowly adapting tonic receptors, I'm wondering, like, so for, in this case, I take care of residents, and they develop pressure sores. So is what's happening to their, in this case, bottom usually, is it, I guess, action potential of the stimulus decreasing for them so much that it's literally died off? And you said eventually we just kind of ignore it, we learn to ignore, like, the physical feeling.
Of laying in bed?
Yeah, so like they're laying in bed in the same spot all the time. The pressure is constantly there. We normally, if we feel something and it becomes uncomfortable, we turn, but they don't turn. So is what's happening, like, is the reason why the area is dying off partially because we're losing the sensation? Because a lot of them can't feel it after a certain point. Like, they can't feel that.
Well, that has more to do with these other types of receptors. We'll also remember that most all receptors are somewhere in the middle here. And so all of them are going to adapt after a while. And to some extent they act as tonic receptors in the very beginning. It's just how long do they keep responding for, right? And so in that case, if they're sitting in bed in the same position for a week, well, after a couple hours, they're not even going to feel it probably, right? And so their receptors are adapting to it.
Does the receptor actually die out after a certain point?
No, the cell doesn't necessarily die. It doesn't have to for this to occur. It just stops sending a message on. It just sort of accepts, all right, this is the new norm. I'm going to stop telling the central nervous system about this. Right. And so if we look at these fast adapting or phasic receptors, it might give us a better feel for how this works. These receptors, they signal changes in a stimulus. Signal changes in a stimulus. So when a stimulus comes on, they'll say, hey, stimulus just started, but they don't keep sending messages. Right? They adapt relatively quickly, meaning they stop sending messages on, even if the stimulus persists. But then when the stimulus stops, they send another message over, hey, something just changed. Okay. So here's a graph that shows that. We don't have the stimulus on this part of the graph, but the stimulus would start right here, it would persist, and then it would stop over here by the second bump. And so with these phasic receptors, you get a receptor potential, gradient potential at the very beginning when the stimulus started, and then nothing until the stimulus stopped, and then you get another message. And you get action potentials that correlate with that. So a way to sort of get this in our heads to think about it is, you could think about stuff that you do all the time or that's consistent and you don't necessarily think about it all day long. For instance, like wearing underwear, right? So right now, I know I'm wearing underwear, but I can't feel it. Right? How do I know I'm wearing underwear? Well, I kind of remember this morning where I got in the shower and put on my underwear, right? And I assume that between when I put the underwear on this morning and now, nothing really weird happened, and it's still there. Right? I can't feel my underwear. I can now that I've been talking about it, I'm going to move around. But before I brought it up, you probably couldn't feel your underwear. Right? It's because the touch receptor is involved there. They send information in the beginning, go, yeah, you remembered your underwear today. And then they stop sending messages. Right? And you just assume it's going to stay on there. If all of a sudden your underwear disappeared, that would be a weird feeling. And you would know about it, and you'd send a message and go, whoop, hey, something just changed, I don't feel it anymore. Right? And so those receptors act more like basic receptors. Yeah?
Is that why in the shower you don't feel every droplet of water when we're in the shower? 'Cause
Could you imagine if you did? Showers would be horrible. Right? That would be too much. So why don't you feel every droplet? That has to do with the sensitivity of all the different touch receptors and your consciousness tuning that out and you adapting to it. So there's a number of things going on there. A lot of stuff you tend to tune out, especially if it's regular things. The first time you ever took a shower, you probably thought, wow, this is crazy, all this water hitting me. And then, after a week, it's like, whatever.